In this video, we shall look at first-order differential equations. A differential equation is an equation that contains differential coefficients. Here is an example. dy dx equals x squared minus y. So this is an example of differential coefficient. This equation is said to be ordinary differential equation because it contains ordinary differential coefficients as opposed to partial differential coefficients. Also, the order of a differential equation is the order of the highest differential coefficient it contains. For example, the highest differential coefficient for this equation is this term, and the order is 1. For that reason, we say this is a differential equation of first order. So let's say you have another equation in a following form. dy dx minus 2 d2y dx squared equals x squared minus y. So this is the highest differential coefficient and the order is 2. So this equation is an equation of second order, a differential equation of a second order. Now a few words about solution of an ordinary differential equation. If x and y are the variables in an ordinary differential equation, the most general relation between x and y that satisfies the equation is called the general solution. When we find this general solution, we are set to solve the equation. Let's look at the following example. Let's assume we want to find the general solution of this differential equation. This is a first-order differential equation. We know that we can rewrite this equation in a following form. If we integrate both sides, the right-hand side will simply become that. The left-hand side is simply y. So the right-hand side is 2x squared over 2 plus an integration constant, let's call it a. So your general solution is x squared plus a. So that is the solution to this differential equation. What about this differential equation? Now we can rewrite this line in a following manner. dy over y equals 2 dx. Now integrating both sides, we will get natural log of y for the left-hand side, and the right-hand side is just 2x plus an integration constant, let's call it c. And therefore, y is just e to the power 2x plus c, which we can write as b e to the power 2x, where I have taken b to be e to the power constant c. So this is the general solution to this differential equation. You see that in the examples above, an arbitrary constant appears in the general solution. A in problem 1 and b in problem 2. Let's try to find the general solution to this first-order differential equation. Rewriting this equation in the following form, we have dy over secant y tangent y equals dx. The numerator on the left-hand side is just 1 over cosine y times sine y over cosine y. So the left-hand side will simply become cosine squared y over sine y dy. In order to determine the general solution, we need to integrate both sides. The left-hand side is simply 1 minus sine squared y over sine y dy, and the right-hand side is integral of dx. So the left-hand side will become the integral of cosecant y, that's the first integral, minus the integral of sine y dy. The right hand side is just x. Let's first do the first integral. It simply becomes dy over sine y. That's what it is essentially. We can reduce this into the following form. dy, using trigonometry identity, it is sine y over 2 cosine y over 2, which we can rewrite or rearrange that in a following form. Have secant squared y over 2 dy over tangent y over 2. You immediately see that the numerator is a result of a differentiation of the denominator with respect to y. So immediately you see the answer will turn out to be natural log of the denominator, which in this case is tangent y over 2. And that's the answer. So the first integral will give you natural log tangent y over 2. Integrating sine y with respect to y will give you minus cosine y. That minus will kill this minus and will give you plus cosine of y plus integration constant equals 2x. And this is the general solution of this first order differential equation. And you note this general solution contains an arbitrary constant a. In next examples, we shall talk about particular solution to differential equations. So what is this particular solution as opposed to general solution? Any particular relation between x and y that satisfies a given differential equation is called a particular solution. In order to get particular solutions, we need to find the values of arbitrary constants that were part of general solutions. So how do we do that? This can be best demonstrated using examples. Let's look at the following differential equation. In addition to the differential equation, we are given a set of conditions. The condition says when x is 0, y has got to be 0 as well. So this put a sort of restriction on the general solution. And when we do that, we can find the value of arbitrary constants. And this is how we do it. Let's first find the general solution. By rewriting this equation in the following manner, just as we did before, we get this. Now let's integrate this line. The left-hand side will give you minus natural log of 3 minus y. This is just a standard integral. The right-hand side is x. But do not forget a constant. Let's call it c. Now that means natural log of 3 minus y equals the arbitrary constant c minus x. So 3 minus y is exponent to the power c minus x, or y is 3 minus e to the power c minus x. Let's use this set of conditions to determine the constant c. We are told that when y is 0, x is 0, or when x is 0, y is 0. So putting the condition inside this equation, we get y is 0 equals 3 minus e to the power constant minus 0. So e to the power c is 3. Substituting back this information in here, we get y equals 3 minus e to the power c is 3 e to the power minus x. So this is the particular solution of this first order differential equation under this set of condition. Such a condition is known as initial conditions. Let's look at another example. We want to find solution to this differential equation given this set of conditions. So first we proceed to determine the general solution, in terms of arbitrary constant, and the above equation will turn into that. By integrating both sides, we get the following. The left hand side is y to the power minus 1. Don't forget the minus. The right hand side is just x plus an integration constant. Let's call it a. Let's rewrite it a little. The left hand side is minus 1 over y. The right hand side is x plus a. Now let's apply the initial condition that we are given. When y is half, x is 0. So that means a is just minus 2. You see, immediately the solution will become a particular solution in a following form. Let's try to express y in terms of x. So we know 1 over y is 2 minus x, so y is 1 over 2 minus x. So you see, once the arbitrary constant was determined, namely when a was found to be minus 2, all the arbitrariness has been removed and you get a particular solution to this differential equation under that initial condition, and that solves the problem. Finally, let's look at this differential equation. dy dx equals to sine x under the initial condition as such. So rewriting it, you get sine x dx. Now let's integrate it. The left hand side is y. The right hand side is just minus cosine of x plus an arbitrary constant. Let's call it e. Let's bring in the initial conditions. When y is 0, x is 0. Or when x is 0, y is 0 plus e. Cosine of 0 is 1. So you see that e minus 1 is 0, or e is just 1. So our particular solution is this. As we have noted, particular solutions are dependent on initial conditions. So when initial conditions are changed, then the particular solution can potentially change. As an example, let's take the following conditions instead. When x is pi over 2, y is 0. Then what is our particular solution? How does it look like? So you see, y is minus cosine x plus an arbitrary constant. Let's call it f. So when y is 0, because x is pi over 2, or when x is pi over 2, y is 0 plus f. Now cosine pi over 2 is 0. That means f is 0. So under a different set of initial condition, the arbitrary constant has a different value, 0 in this case. So the particular solution becomes just that. So you see how the particular solution is dependent on the initial conditions provided. Please don't forget to share, like, and subscribe if you find this video useful. Thanks for watching.